Yeah. So you had a question from 3 lectures ago. What is the question?
I was talking about the operator having an eigenvalue thing with the student tutor, and she said the eigenvalue I get after acting the Hamiltonian operator is energy eigenstate, not energy. Could you please explain what's the difference of energy eigenstate and just energy in classical sense?
Sure. Yeah. Like, classically. So okay. So if you were looking at things classically, then the state of the system is described by a point in phase space, right? Okay, so this is your phase space. So it has, it has coordinates such as the generalized coordinates as well as the generalized momenta. And if you have a point on your phase space, this gives you the state of the system. And if you have a Hamiltonian, Hamilton's equation, which are also equivalent to Newton's equation, they tell you how this point is going to evolve in phase space. Just 1 second. Okay, so classically, that's what we mean, right? And this, and we can associate an energy with this point, and that is the energy of the particle. And if the Hamiltonian is time independent, that energy is going to be conserved, right? So classically, we know what a state is. The state is the coordinates in phase space, right? And that changes with time as the system evolves, okay? And energy is E is defined by the value, the numerical value of the Hamiltonian function, okay? Does that make sense?
Yes, sir.
So that's classically. So quantum mechanically, what happens is this. So quantum mechanically, the state, there is no such thing as a phase space. Phase space doesn't exist, okay? And that's because position and momentum cannot be simultaneously defined, okay? So instead, state of the system is given by a vector in an infinite dimensional vector space with a positive definite norm, okay? And this vector space, the technical name for it is called Hilbert space, okay? So, and now we can think of this vector psi, the vector, and the components we can think in terms of its spatial label x, okay? So this is the state at some time, say t. So this is the state of the system, okay? So state of the system is an abstract vector in an abstract vector space. Okay, so this is a mathematical object. A priori, it doesn't have anything obviously physical about it, but according to quantum mechanics, this state, this function, so it's a function, this state, when we look at this state in the, in the position basis, so then, okay, sorry about that. Did I lose you guys? No, I didn't. Okay. Yeah. So, okay. So as I was saying, so this state is also known as the wave function. Okay. Okay. So far so good.
Yes, sir.
Okay. Now comes the interesting part. In the classical case, what happened was that if I give you a point on the phase space, then the evolution of that system was governed by Hamilton's equation, which are equivalent to Newton's equation, but formulated in terms of the Hamiltonian. So what happens in quantum mechanics is that how does this state evolve with time? Well, it's given by the Schrodinger equation. So if our Hamiltonian is time independent, so if H is time independent, and this course we will take this to be time independent, then psi at some time t can be predicted from psi at some earlier time, say t0, by applying to it the Hamiltonian, the time evolution operator. Okay. This is the solution to the Schrodinger equation, the formal solution. Okay. So we now have the analog of evolution. Now, what is energy? So, H is an operator. Okay. It is a differential operator that acts on wave function. See, in classical mechanics, H was a function of space and momentum, of position and momentum. And because it's a function it was a function also of time, at every moment in time, it took a particular value. So for example, on this, if the system was actually insulated from outside world, if you take the system to be large enough or isolated, then, you can show that the energy was conserved. And therefore, in this evolution, on this path, the numerical value of H would be different. Why am I putting emphasis on the numerical value? Because if you look at H, say for a simple particle, it would be given by p squared by 2m plus some potential energy. Now, this is classical, okay? Now, as your particle is moving in space, the x is changing. So maybe I should use q here. For configuration, generalized coordinate. So Q is changing, right? So therefore, the potential energy is changing. And if the potential energy is changing, the momentum is also changing. But your energy, the value, numerical value of energy is not changing because of conservation of energy when there is no time dependence. So the functional dependence on the numerical value of P and Q is changing, but numerically H is not changing. And that is what we call energy, right? So energy is the numerical value of this function. But in quantum mechanics, H is an operator. An operator is like a matrix, an infinite dimensional matrix. It doesn't have any numerical value, right? The whole point of a matrix is it's not a number, right? So yes. How the hell are we going to get something physical out of it? Well, matrices have something interesting. Matrices and operators and operators are characterized by their eigenvalues, right? And we know that these eigenvalues are, so these eigenvalues are basis independent, right? But the eigenvalues also are solutions to this equation. If O is an operator, psi n, if a n is an eigenvalue, they are solutions to this equation. Okay, and this is known as an eigenvalue equation. And if a n is an eigenvalue, then there is a corresponding vector or a state attached to it, and that's called an eigenvector. Okay, eigenvector or eigenfunction. Okay. Now it is, if O is a Hermitian operator, if O satisfies this, then we prove the theorem that A, N, they are real. Then it's a postulate of quantum mechanics that if I measure, so if the system is in an eigenstate of O, say psi of M, then the result of an observation will yield AM, the eigenvalue, with 100% certainty. So, but if the system is in a different state, say in a state such that it is not an eigenstate, say it's something like C1, psi1 plus C2, psi2 dot dot dot, Cn psi n, then you will obtain an, or say let's not put an, say ai, that is one of these, obtain ai as a result with probability ci mod squared. Okay, and that's the Born interpretation. Okay, does that clarify things?
Yes, sir.
Okay, all right, any other questions?
So did you explain the energy eigenstate here?
Yeah, I mean, if you take O to be H, the Hamiltonian operator, then everything, then the AN, those numbers will become the energy eigenvalues. And the eigenvalues are the result of your experiment. Those are the possible energies of the system, okay?
Okay, got it.
Okay, any more questions?
Actually, I have another, but it's small. The question is,
Yeah,
if we have momentum space and position space, do we also have spin space or energy space? Those are observables as well.
exactly, yeah, yeah. In fact, it's, as I said in a previous class, space is essentially, the more mathematically sophisticated way of thinking about is the following, that you have only one space, okay? one big Hilbert space. Sorry, Hilbert should not be spelled like that. So one Hilbert space, and so it's an infinite. It's typically an infinite dimensional vector space. Although, you know, depending on the degree of freedom that you're observing, you can project down to a finite dimensional subspace. So this is a representation of an infinite dimensional. You know, so there are lots of axes, and you have some state psi which represents the state of the system. And what time evolution does is that it's rotating this this vector in some way according to some Hamiltonian. Okay. Now, if you are, say, looking at the system in terms of the eigenvectors of, say, the position of the H operator, energy operator, then what you're doing is that you're choosing a basis for this Hilbert space. But you could have chosen a different basis, a basis which are the eigenstates of the position operator or the momentum operator. So all these different, all these different operators, they furnish a different representation of the same underlying Hilbert space, okay? So does that make sense?
Yes, sir. So the spaces are just our choice of basis.
Exactly, yeah. These are our choice of basis. So they're all equivalent to a large extent. There are mathematical subtleties, but in a first course of quantum mechanics, it's not a good idea to formulate things mathematically. In the second course, once you've seen all of this, you're experienced with some of the physics, then one can get into a more mathematical definition. And it's actually a very beautiful mathematical formulation. It was first formulated by Dirac and then put on a rigorous basis by Johnny von Neumann. Okay, any more questions?